SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 2, that is Vapor Power System Part 1. So, in this lecture we are going to cover the following topics. So, in our previous lecture we covered about the Rankine cycle. Here we will see that how performance enhancement can be done for a Rankine cycles. Under this segment we have three important cycles for vapor power systems. One is superheat cycle, other is reheat cycle, third one is regenerative cycles. More elaborate mathematical modeling and thermodynamic analysis will be covered in these lectures. So, let us see first thing is that why there is a necessity for enhancing the performance of a Rankine cycle. So, first of all, when you dealt with the Rankine cycle, an ideal Rankine cycle, we say that saturated steam at state 1 expands in the turbine. So, through this process and during this expansion process, we land off at the exit of the turbine, the steam quality to be not par with respect to operating requirement for the turbine. In general, turbine blades are designed to operate the steam in vapor state, but if the quantity of water vapors or quality of the steam is not adequate, then it normally erodes the turbine blades. For that reasons, the turbine blade degrades. Now, when it degrades, to overcome this problem, what we thought of is that steam quality is retained at least 90% in the turbine exit. So, if you want to retain the steam quality of the turbine exit, that is state 2 or 2 double dash, then we must push this fellow, that means inlet state, to somewhere in this domain. That means one should be pushed up to the superheated region. And when we say it is a superheated region, so thereby what advantage we get is that after expansion the quality of the steam always remains in the vapor regions. That is one aspect. Second aspect, that when you do the superheating, we are actually going for the mean temperature of heat additions for the fluid. Through this process you have the higher work output, because another important aspect is that when you go to the superheated regions, this due to the divergence of the constant pressure line, this difference, that is delta H, becomes progressively higher if you handle the steam in the superheated regions. And here two things gets ensured through this superheating. One is higher expansion work in the turbine. Second is quality of the steam becomes at least more than 90%. The other method of increasing the thermal efficiency of vapor plant is providing a regenerative feed water heating or regenerations. So, this thermal circuit diagram will revisit subsequently, but here through this regeneration what we essentially do is that if you consider the ideal cycle, that is 1, 2, 3, 4 A and 1, and another's, or either you can say 1 dash, 2 dash, 2, 3, 4 A and 1 dash. In any of the cases, what we actually do in the regenerative system is that we take some fluids you take some fluids outside of during the expansion process, you take some fluid out, and suppose during this expansion process from 1 to 2, 1 unit of fluid is entering, and you tap y amount of fluid or steam through another process. So, that is what we call as a feed water heating systems, and rest of the things we expand in the turbines. So, through that process what actually goes into the boiler is that a thermodynamic states which is 4A, which is in between the state 4 and state A. So, through this regenerative methods, we are actually increasing the mean temperature of heat additions. In fact, this is more logical in many of the senses, because most of the times we have exhaust streams coming out at various locations in the power plant, and those exhaust streams can be tapped to do this kind of heating systems. So, this is this particular method we call as feed water heating systems or regenerations. It can be an open system or it can be a closed water feed water heater. Then let us first see the first important modification that we do in the Rankine cycle, which is superheat cycle. We already mentioned that quality of the steam at the turbine exit should be at least 90%. How we need to do the superheating arrangement is like this. Your in a conventional cycle, which is 1, 2, 3, 4, A and 1, it operates at a state when the steam is at saturated vapor. Now, through this superheating process, what it says is that once we reach the state during the heating process in the boiler, that is from 4 to 1, when heat is added till we reach the state 1, but in a superheating systems we say that keep adding heat to the steam, and so that we reach in a region which is called as a superheated region, or this, that means if you say this is liquid plus vapor, this is pure liquid and this is only vapor regions, and we call this as a superheated vapor. So, through this process, once you do this, now at the state 1 we expand the steam in the turbine, so that we land off the exit condition of the turbine as 2 dash, and obviously quality of 2 dash is greater than quality of 2. So, if I say quality of steam at x 2 dash is always greater than x 2. So, through this process we solve the problems of not getting eroded of the steam turbine blades. Now, coming back to the boiler sides, so the essential or extra arrangement that we do is that we need to have another unit called as a superheating unit, and the boiler and superheating unit combinedly is called as steam generator. So, we look into the steam generator in more details in the subsequent modules. For the time being, we just have to understand the steam generator term is nothing but the which includes boiler and superheating systems that supplies necessary heat to the working fluid. So, from subsequent onwards, we will now see that only superheated cycle can give you a better thermal efficiency. The another part is a reheat cycle. So, ideally speaking, reheat cycle and superheat cycle, they run in parallel, because normally we take the advantage of this reheat, because what we do is in the reheat systems is that first, if you look at this particular arrangement, a reheating system unit, in a reheating system unit, the expansion process in the turbine is done in 2 or more phases. So, first phase is called as high pressure turbine, second phase is called as low pressure turbines. So, let us understand how we achieve this. So, once the steam from the boiler at state 1 stands for at this state superheated region at temperature T1, it enters to the high pressure turbine unit. Now, after the expansion in the high pressure unit, so state goes to 1 to 2. So, the thermodynamic process of expansion or isentropic expansion from 1 to 2 takes place in a high pressure turbine. At point 2, the steam is again reheated. So, instead of expanding further, it is reheated, and when it is reheated, it goes to the state 3, and this reheating systems happens in the again in same boiler unit. So, but however, while doing this reheating, we necessarily do not go to the state point 1, somewhere less than that. So, the state point 3 is T3 is less than T1. Now, the steam at state 3 enters to the low pressure turbine unit, and it expands to this low pressure turbine units. So, there are work output happens in H1 minus H2, the first part, and second part is H3 minus H4. So, these two additionally things it enhances the work output. So, this is the advantage what we get in a reheating process. So, ideally speaking, then from 4 the system goes to 4 to 5 in a condensing unit, 5 to 6 in the pump, and again from 6 to 1 it goes in a boiler. So, this is all about the reheat cycle. Now, there is another concept of called as supercritical reheat cycles. So, what we understand the supercritical system is that for every working fluid or pure substance, it has the thermodynamic diagrams like PV diagram, TS diagram, it shows the various states. That is, for example, in this for steam, if you draw the working fluid, the state of the working fluid in a TS diagrams, we have liquid regions, we have liquid plus vapor regions, then we have vapor regions. Now, while operating the reheat cycle or normal reheat cycle, we really do not go beyond this saturated dome. So, this classical process of going to this is that the state of the system goes within this liquid vapor regions, and that is happens in a constant pressure line. Now, what the supercritical system tells is that you increase the pressure such a way that we cross this critical point, so that the liquid directly goes to the steams without crossing these liquid vapor regions. That means, in this boiler arrangement, which is our steam generator unit is equipped in a such a way that we create a pressure and such that liquid water goes directly to the steam, and that means in that case we have to operate the pressure at which it is above the critical pressures. Now, for water this critical pressure is 22.1 megapascals. In other words, it means that you retain the pressure in the steam generator which is about 22 megapascal or above. Through this, if you can do that, then from 6 to 1 we can directly reach in a cycle which is called as supercritical cycles, and essentially this cycle does not cross the liquid vapor regions. But these have although there are infrastructure difficulties, but they are higher efficient than the conventional reheat cycles. And for a supercritical cycles, we need to have a combustion process which can be achieved through pulverized coal or coal powder and specialized steam generators. Now, just to give you some brief idea that what advantage we get using a supercritical reheat cycle is that if you use a conventional steam reheat cycle, then maximum efficiency we can achieve is 40% with all types of augmentations. But when you think about a supercritical power plants, so we need to expect that steam generator should operate more than 22 megapascal or above. Now, a closed look or close analysis of thermodynamic analysis reveals that a supercritical power plant which operates at 30 MPa and 600 degree centigrades, if you can design this, then we can achieve efficiency up to 47%. Now, ultra super critical power plant, they again go beyond such pressures, like they operate somewhere at about 35 megapascal and 700 degree centigrades. For that we can achieve efficiency up to 50%. So, except the installation difficulties, supercritical power plants have more advantages as compared to the conventional power plants operating in a reheat cycle. Then we will move on to regenerative cycles. So, we have understood superheat cycle, reheat cycle, then we will move to regenerative cycles. Let us try to understand this reheat cycle. So, before that we have said that we require superheating for the steam to expand in a turbine. So, if you take this as an advantage, then what we can say that during a continuous expansion process in the turbine, that is from 1 to 3, we think of tapping some amount of water or some amount of mixer through some process, and that is essentially achieved through a open feed water systems. What you typically do is that the turbine stage is designed in two folds. One is stage 1 and second is stage 2. We may think of high pressure stage and stage 2 is a low pressure stage. So, while during this expansion process, that means when the steam enters into the turbine at state 1, after certain expansion, that is at state point 2 somewhere here, we tap Y quantity of mass or liquid or steam. We take, suppose from we have 1 unit of steam which is entering, at state 2 we tap Y quantity of steam and allow the rest 1 minus Y quantity to expand in the next stage turbine. And then what we do? So, through and in this condenser process also, that is from 3 to 4, 1 minus Y unit that gets condensed. So, it reaches at state point 4, then from 4 there is a one feed water pump that takes this 1 minus Y quantity of liquid saturated liquid at state 4 to state 5, and then you allow it to enter into a open feed water systems, and through this when you allow to enter to the feed water systems, there it meets Y unit of steam. So, thereby additional heating we get from this steam, and again the combined working fluid, that is Y unit of steam which is entering in this line along this line, and 1 minus Y unit of steam at Y unit of liquid water that gets condensed water, it mixes with Y unit of steam, and the combined system is enters into the boiler at state 7. So, through this process what happens is that your heat in Q in becomes H1 minus H7, Q in dot by m dot will be equivalent to H1 minus H7. So, in that process what happens, your additional load from the boiler is reduced. So, when we have additional load is heat load is reduced, so we have enhanced thermal efficiency of the plant. So, had this process been done without reheating, then from 5 to 1 the boiler would have boiler load would have been bringing the state from 5 to 1. Now, it becomes from only 7 to 1. So, through this process your heat addition into the boiler is reduced. So, this is the advantage that we get in an open feed water systems. So, in practice the operating conditions are such that reduction in heat addition is more than the offsets with respect to decrease in the work output, and there is an enhancement in the thermal efficiency. So, we will see a brief look into the cycle analysis. Here our attention is focused to the mass balance equations that happens when you tap this heat in the turbines. So, we say that at state 1, 1 unit of 1 kg of steam which enters, and at 2 we take out y unit of or y kg of steam, and rest of the steams 1 minus y it is allowed to expand in the second stage turbine. Then subsequently 1 minus y goes into the condensing unit, and ultimately at stage 6 both the fluids mixes and that goes to the state 7. If you can do this mass and energy balance, we can write it for this mass balance, that is M2 plus M3 is equal to M1. So, state 3 is somewhere here, state 2 is this, and so M3 is 1 minus y. So, through this we can find out actually what is y, how much y we are going to get. Now, if you can take a close look of this feed water systems, this energy rate balance we can frame, and through this process we can find out what is the value of y. Then through subsequently in the same procedure we can get turbine work, pump work, Q in, Q out. Now, there is another method. If you look at this open water feed water system, actually there are two pumps, that is pump 1, pump 2, and pump 1 stands for condensing 1 minus y unit of steam, and whereas pump 2 stands for entirely pumping entire unit of the mass that enters at state 6, and it takes these things from this pressure at 6 to the boiler pressure. So, but here in an closed feed water systems, the main intention was that steam is not allowed to mix. So, what it means is that the y unit of steam that comes at state 2 and it does not mix with the condensate that comes at state 5. That means, we are only tapping the heat of the steam, not the mass which is gets mixed. So, there is no mixing is allowed in this closed feed water systems. So, thermodynamically if you look at this diagram, we start with state 1, at state 2 we take out y unit of steam, remaining 1 minus y unit expands in the low pressure turbine. Now, when you are at state 3, at state 3 we condensate this 1 minus y unit through this condensate line. Then what happens to the rest y? At state 7, that means after the y unit of steam enters the saturated liquid, we use a trap system. So, that only traps the vapor. So, thereby the condensate or liquid state comes at somewhere in the state 8. So, entire fluid mix at 8 and then again it goes to the state 4, and the state 4 is nothing but in the condensing unit, and from then entire process is repeated and we get the state 5 as at the exit of the closed feed water systems. And in these closed feed water systems, then from 5 to 6 and 6 to 1 is the heat addition process. So, additionally what advantage we get here, there is no extra additional pump. So, only one pump which is actually used in the conventional power plant, that is sufficient to run this type of system. So, this is all about 3 important cycles, reheat, superheat and regenerative cycles. So, some of the advantage of this reheat cycle I can say is that reheats gives additional benefit of getting more power output and improving the quality of the steam. And again regenerative cycle reduces the heat load in the steam generator and thereby cycle efficiency gets improved. Some of the power plants can operate in both modes like reheat and regenerative modes to get enhancement in both power output and efficiency. And with respect to the closed feed water systems, there are some advantage in this closed feed water system which says is that there is no extra pumping requirement. So, with this I completed this part. Now, at the end of this lecture we will try to solve a numerical problem. So, this numerical problem is based on a Rankine cycle that operates with reheat and superheat. Reheat and superheat I mean we have to draw the thermodynamic cycles, which means that we are operating the steam in the superheated regions and at the same time we need to take the advantage of reheat. So, the problem that gives us is that the steam enters the first stage of turbine at 8 megapascal and 480 degree centigrades, it expands to 0.7 megapascal. So, let me redraw the thermodynamic cycle. So, in a TS diagram, we first define the states. So, we have the first pressure line which is the highest pressure line, which is 8 megapascal. Second one is second pressure line where reheating is done, 0.7 megapascal, and third one is condenser pressure line, that is 0.008 megapascal. So, we are at state 1, that state 1 is 8 megapascal 480 degree centigrades. Then after expanding to 0.7 megapascal, it is reheated to 440 degree centigrades. So, that means we are somewhere at state 3, which is 440 degree centigrades, and state 1 is 480 degree centigrade. The net power output of the cycle is 90 megawatt. So, we get 90 megawatt as power output from the cycles. Each turbines operate with 88% efficiency. So, turbine efficiency is 88%. So, this makes us aware that the state 2 is has to take into account of the isentropic efficiency for the turbine. So, for that reason this is a irreversible process. So, state 2 will be somewhere here, and had it been the isentropic process, corresponding point would have been 2s. Similarly, state 3 isentropic process, and 4 would be an irreversible process, and 4s is 3,4s is isentropic process and 3,4 is irreversible process. So, point 4 is located. Then from 4 to 1 the goes into the condenser and it reaches to state 5. Then at 5 there is a pump that takes this saturated liquid to a boiler pressure, and then from 6 to 1 it goes through this manner. Okay. So, this is your heat addition process Q in 2 WT1, this that is power recovery process WT2, and heat rejection process we say Q dot out, and this is W dot P. So, we have to individually calculate all these numbers. So, this problem is nothing but we have to revisit the steam table, and once you draw this cycle diagrams, it is possible to note down all the thermodynamic states from the steam table. Now, let us see at the superheated steam table at 8 megapascal and 480 degree centigrades, we have H1 is 3348.4 kilojoule per kg, and we also require isentropic entropy value, that is S1, that is 6.66 kilojoule per kg Kelvin. Then from 1 to either you have to go 2s and 2. So, state 2 and 2s, how do you calculate? Now, state 2 and 2s, what we know is they are at 0.7 megapascal, and T3 is 440 degree centigrades. So, this point is also located. So, we can find out at this state things, we have data SF as entropy value in the saturated liquid state 1.992 kilojoule per kg Kelvin. These values we can get from this steam table data. So, we have entropy at saturated vapor state, that is 6.708 kilojoule per kg Kelvin. Again we have HF is equal to 697.22, that is enthalpy value kilojoule per kg, and HFG is equal to 2066.3 kilojoule per kg. So, we have all the data right now here. What we can now find out what is X2S. X2S can be found out because entropy that is H1 S1 is equal to S2S. So, from these things we can calculate X2S as S2S minus SF divided by Sg minus Sf. All these numbers are there. We can find out X2S as 0.9895. Then we have the X2S, then we can find out H2S is equal to HF plus X2S into Hg minus HF. So, knowing all these numbers or inserting all these numbers, we arrive at this enthalpy at state 2s as 2741.8 kilojoule per kg. Now, to get back the information of state 2, we have to rely on isentropic efficiency of the turbine. So, let us go to the basic definition, what is isentropic efficiency for the turbine, and in this case it is H 2 minus H 1 divided by H 2s minus H 1. So, that is equal to 0.88. So, you know all these numbers. So, we can say H 2 is equal to H 1 plus 0.88 into H 2s minus H 1. So, this value we can get as H 2 is equal to 2814.6 kilojoule per kg. So, we know the state 2 and 2s, then we will have to move to state 3. So, state 3 is nothing but the entry stage of the low pressure unit of the turbine. So, for that what data we know is that P 3 0.7 megapascal and T 3 as 440 degree centigrades. So, this is a superheated region. So, superheated steam table will implies you have to rely on the data from the superheated steam table at 0.7 megapascal and 440 degree centigrades. So, this will give you H 3 as 3353.3 kilojoule per kg and S 3 is equal to 7.757 kilojoule per kg Kelvin. So, you have to repeat the same process for state 4s and 4. Because those are expansion process. So, P 4 we already know it is condenser pressure, it is 0.008 megapascal. S 4s is equal to S 3. So, this will give you S 4s X 4s is equal to S 4s minus S F S 3 S g minus S f. Now, at these pressures we have these data. S f is equal to 0.5926 kilojoule per kg Kelvin, S g is equal to 8.2287 kilojoule per kg Kelvin, H f is equal to 173.88 kilojoule per kg, H f g is equal to 2403.1 kilojoule per kg. So, inserting this number of number for S f and S g, we get X 4s as 0.9392, which clearly says that the exit state is more than 90%. So, this advantage we get through this reheat and superheat. And similarly, we can find out H 4s, that is H f plus X 4s into H g minus H f. inserting these numbers we arrive at H4S is equal to 2428.5 kilojoule per kg. So, we know this efficiency for low pressure turbine as 0.88. So, write down that equations H3 minus H4 divided by H3 minus H4S, that is 0.88. So, we have 4S H3, and from this equation we can get H4 as 2539.5 kilojoule per kg. So, we have all the state we know the state condition of 4S and 4, then we are left with 5 and 6 conditions, and that is nothing but for the pump. And the pump operates at a means you have to find out the saturated liquid state for the pump, which is operating at 0.8 megapascal from condenser pressure to the boiler pressure of 8 megapascal. To do that, we need to revisit data for saturated liquid at 0.008 megapascal. So, we have H5 is equal to 173.88 kilojoule per kg. Then at that point we have specific volume, it is 1.0084 into 10 to the power minus 3 meter cube per kg. Then we can use the pump equation as H6 is equal to H5 plus V5 into P6 minus P1. So, we have P6 8 megapascal, P1 P6 is 0.008 megapascal, P1 is 8 megapascal. So, knowing this number, we have H6 as 181.94 kilojoule per kg. So, we have till this point of time we have all the data for this or the thermodynamic states. Then we have to relook into the part by part analysis. First one is thermal efficiency, mass flow rate of steam, heat transfer into the working fluid, into the boiler and condenser. So, let us see what is the thermal efficiency, and that is nothing but W net by Q in, and that W net is W dot T1 plus W dot T2 minus W dot P divided by Q in, and that is, if you write down each of the term, turbine work, two parts. For the first state turbine, it is H1 minus H2. For the second state turbine, it is H3 minus H4. For pump work, it is H6 minus H5. Heat addition process goes in two parts. One is H1 minus H6. Second part is for reheating, that is H3 minus H2, and all the numbers are we have evaluated, and this part we rewrite as 1339.6 divided by 3705.2. So, this part goes as a W net, this part goes as Q in, and efficiency is about 36.15%. Second part is mass flow rate of steam. So, for mass flow rate of steam we know that net power is 90 megawatt. So, cycle work is equal to m dot into w dot net, that is equal to 90 into 10 to the power 3. So, w dot net is 1339.6. So, this will give you m dot as 67.2 kg per second, or approximately 2.4 into 10 to the power 5 kg per hour. Now, heat transfer into the working fluid in the boiler. So, we say Q in, which is boiler. They have two parts, one is conventional, this is from taking from 6 to 1, other is from 2 to 3, that is reheat section, that is m dot into H 1 minus H 6 plus H 3 minus H 2. So, this number is there in the denominator. So, we know m dot, that is 67.2 into we know this number 67.2, and this number we have already found out. So, 67.2 into 3705.2. So, this is 248,986 kilojoule per second, or it is approximately 249 megawatt. And similarly, Q dot out, which is in the condenser, that is nothing but m dot into H 4 minus H 5. So, this is 67.2, H 4 minus H 5 is already evaluated, that is 2539.5 minus 173.88. So, this number is 158,970 kilojoule per second, or approximately 159 megawatt. So, a summary that we can make out is that we have supplied 249 megawatt of energy to produce the work of 90 megawatt, and in this heat rejection process we have rejected 159 megawatt. So, this process leads to overall efficiency of about 36%. So, this is a realistic scenario for a steam power plant that operates with reheat and superheat mechanism. So, with this I conclude. Thank you for your attention.